Hello and welcome to the 25th class of this course. So in the last class we learned about the relation between the group theory and quantum mechanics, and there we saw that the wave functions which are eigenfunctions of any given operator, for example like Hamiltonian operator, which is an energy operator, can act as the basis of for the irreducible representations for any particular molecule belonging to a particular point group. Also we learned about the direct products of the irreducible representations, which will be extremely useful in the coming weeks, and we also learned how these direct products are used. Okay, they can be used. So we took an example to show that direct product can be used to find out the energy elements, and also to find out the spectral intensity, more precisely the probability of a transition, whether it's allowed or disallowed, and if it is allowed, then in which particular polarization it will be allowed. Now one thing we didn't talk about in the last class, that not only the wave function, which is an eigenfunction of an operator, can form the basis for irreducible representation, but also the linear combinations of the wave function can also act as the basis for the same irreducible representation, which is quite understood, because if I have an eigenfunction psi I for an operator, say H, the Hamiltonian, then I can express psi I as a linear combination of various size. So therefore, it's no wonder that the proper linear combination of the eigenfunctions can also act as the basis of the irreducible representation, and this property is of utmost importance when we try to find out which kind of say atomic orbitals will combine to give molecular orbitals, or which will contribute toward the hybridization of the orbitals. Also to find out like which particular bond vectors will combine to give an internal motion like vibration. So in general, the chemists, they try to use the symmetry restrictions and to facilitate themselves to understand chemical bonding and molecular dynamics. For example, as I said, constructing hybrid orbitals or molecular orbitals, or finding proper orbital sets under, say, a ligand field, or also analyzing vibrations of molecules. Now, in order to do that, that is developing such understanding based on symmetry restrictions, one faces a common problem. The problem is that one needs to take one or more sets of orthonormal functions as required by both group theory and quantum mechanics. And here these orthonormal functions, in case of these chemistry problems, these functions are taken to be the atomic orbitals, okay, or in case of vibrational motions or the other internal motions, the internal coordinates of a molecule. And in order to make a proper combination which will keep the resultant function orthonormal, and that will act as the basis of irreducible representation, one needs to be quite careful in his formulation of the problem. And as we learned in the last class, this kind of the relation between the quantum mechanical observables, rather the wave functions, rather not the observables, and the symmetry constraint is really is important for solving this problem. Okay, so in case of when one tries to find out which atomic orbitals will form the hybrid molecular orbitals or in general molecular orbitals, one needs to take care of the symmetry constraints, and then ultimately the linear combination that one gets is known as symmetry adapted linear combination, or in short SALC. So, or in short, so how one can find out that which orbitals will be able to combine in a linear fashion and keeping the symmetry constraints to give a proper basis for a particular irreducible representation of a particular point group to which our concerned molecule belongs to. Now, you see why the symmetry constraint is needed, because for example you take any given molecule, say for example ammonia. Okay, so in case of ammonia what we have is this bond that we write, right? Now the bond means what? This is the combination of the atomic orbitals. So hydrogen has 1s orbital and nitrogen has 1s, 2s, 2p orbitals. So which orbitals will combine to form this successful bond is not only governed by the energetics but also governed by the symmetry. So until and unless the orbitals of these atoms have the same symmetry, they cannot combine. So there is a symmetry restriction, and therefore the the combination that we will form to facilitate the bond formation will be a symmetry adapted linear combination of atomic orbitals. Okay, so how do we do that? So there is a fundamental tool which is universally accepted, and this particular tool is known as projection operator. So now we will learn about this particular projection operator, which will help us in finding out the SALCs, okay, for any given molecule. In order to understand the projection operator and its functioning, we better learn how to get this projection operator first, and then we go for the actual application of this projection operator by showing some illustrative examples. So let us start with, let's assume that we have an orthonormal set of Li number of functions. Okay. Such as phi 1, phi 2 up to phi Li. Okay. So we have Li number of such functions, and we also assume that these functions form the basis of the ith irreducible representation of a point group to which our concerned molecule belongs to. Okay. So if this forms the basis for an ith irreducible representation, so we will put a superscript as I. Okay, that will tell you that to which irreducible representation these functions act as basis for. and the order of the group that we are concerned, let's take as H as usual. Now, if I consider any operator, any symmetry operator as R, and I take any one of these functions and operate any symmetry operation on that function, then what should I get? So, if I take any arbitrary function phi t is one of these Li number of phi's which form the basis for ith irreducible representation. So, that I can write as right. So, I can write this one as I have taken these functions to be the basis for ith irreducible representation, and this gamma r having superscript I is the representation for this particular symmetry operation R giving ith irreducible representation, and ST you can understand is a particular element. Okay, so this gamma r is the matrix representation. So ST gives me the particular element of that representation. All right. So now what we have to do in order to find out how to get the projection operator, what I will do, I will multiply both the sides with another representation for a jth IR, say. So, I will multiply both the sides by a quantity which is gamma of the same operation R and belongs to jth irreducible representation and some element S prime T prime. Okay, and I will take a complex conjugate of that particular element, and after that we will sum it over all the symmetry operations R. So, we will have to do the same thing on the right hand side as well. So, in that case I have summation over R, summation over S, phi I S gamma of R ST multiplied by gamma of R for jth irreducible representation having elements S prime T prime. Okay. So, now one thing you notice here, this phi is a function. So, it is independent of the symmetry operation, right. So, it does not clash with the symmetry operation. So, I can very easily separate this phi part and this representation part. Okay. So, what I can do, I can rewrite this one as summation over S phi S I and then summation over R and this part, that means gamma of R for ith irreducible representation and element ST multiplied by gamma of R for jth irreducible representation having element S prime T prime and take the complex conjugate of this one. Okay. So, this we can very easily do, right. Now, we have a situation where this right hand side tells me that I have I can have such Li number of such products, okay, where each one will be a function phi S that belongs that forms the basis of ith irreducible representation and that is multiplied by a coefficient. Okay. So, this part is a coefficient which is multiplying this phi s, okay, and I can get such Li number of products. Fine. So now, if I consider this particular coefficient, what does this coefficient tell me? So this coefficient themselves are the summation of the products of two irreducible representations over all the symmetry operations. That is what it tells me, right. Now, such sum of the products of irreducible representations over all symmetry operations are governed by the great orthogonality theorem. So, what does the great orthogonality theorem tells me about such a coefficient? Okay. So, if I just take this one, so it is sum over R, gamma of R for ith irreducible representation and having elements S and T multiplied by gamma of R for jth irreducible representation having elements S prime T prime is equal to, if you remember the great orthogonality theorem that we have discussed earlier, so we have considered the order of the group to be H. So here is the order of the group, and then I have two different irreducible representation, ith and jth, right. So their dimensions, let us assume Li and Lj. Therefore, this will have Li and Lj, all right, and then I will have a series of delta functions. So here what we have two different irreducible representation, okay. So great orthogonality theorem will guide you how you can write the delta functions here. So for two different irreducible representation, I will have delta Ij, and then I have elements as St for the ith and S prime T prime for the jth irreducible representation. Therefore, I will have two more delta functions. One will be delta S S prime and other one will be delta T T prime. All right. So now, what does that tell me? It tells me that I can replace this one over here, right. So this part will remain as it is, and I can write here as summation over S phi S for ith reducible representation and H by root over Li Lj, and then three delta functions, right. And then whatever I have on the other side, that remains. So here this right hand side immediately tells me that phi s will, this side actually will give a non-zero value only when this S is equals to S prime, right. I am summing it over S. So if I operate this operator on this particular function phi t for an ith irreducible representation, then I will have this right hand side having non-zero value only when S is equals to S prime. So I will get phi S prime here with two more delta function, delta Ij, delta Tt prime. So which means that not only that it has to be a particular function phi S prime in order to have non-zero value for this part, but also the two irreducible representation that we are considering here must be identical, meaning I equals to j, and the other element also should be the same, that is t equals to t prime. So therefore, if I consider all this, what do I have is following. So what we have here, the left side sum over r, I can just slightly rearrange because these two are not interfering to each other. So I will write this term first. So I have gamma of r for jth irreducible representation having elements s prime t prime multiplied by the operation r, and acting on phi t forming basis for ith reducible representation. Okay. So this is equals to, from here whatever I said, if I can write that h by Lj, because when I equals to j, then only this right hand side will survive. So therefore, for I equals to j, I have Li equals to Lj. So Lj square and take a root, I get Lj. Okay. So this and I have phi. Now s prime, because for s equals to s prime, this will survive, and for ith reducible representation, and if I still keep the deltas to keep the generality still, I will have this part. Now by rearranging, I can have Li by h, whatever we had, phi of s prime I delta ij delta tt. All right. So this this part of the left hand side is known as the projection operator, and this is abbreviated as P of s prime t prime, okay, for jth irreducible representation. Okay. So this is equals to the projection operator, and then you have this fine. So this is my projection operator. So now you can see here that this particular operator, when it is operated on any arbitrary function phi t, it projects out another function phi s prime. Okay. So this projection will take place only when this function phi t contains or it itself is phi t prime. Okay. So then it will give it will survive. Okay, because I have this delta function delta t prime. Moreover, it has to belong to the same particular irreducible representation. Okay. So then I can have this phi s prime being projected out from an arbitrary function or the combination of functions which is given by phi t phi t. All right. So, ultimately, by taking care of these delta functions, what I can write is this maybe. Okay. So, I will rub this part. So, therefore, what I can write is P of acting on a general function, any arbitrary function t, which will give me ultimately phi t prime if I take care of this delta t t prime, right. So, essentially it means that this phi t must contain some component of phi t prime. In that case, I will have then phi t prime, and for any arbitrary any irreducible representation J, I can write this general form of this. Okay. Now, this is the most general form, but I can have the special case. So, the special case is as follows. So, if I take this so, this is a particular special case that we can consider. So, what does this special case tells me? So, it tells me that this p j t t prime, okay, that is the projection operator which will project out phi t prime out of an arbitrary function which is phi t that we started with, right. So, by using Li such projection operators based on Li diagonal matrices, okay, so matrix elements rather, we may generate from some arbitrary function which is phi t that we discussed, as a set of functions which will form the basis of the jth irreducible representation. Okay, so this is what we have as a projection operator. Now, these projection operators will be used in specific cases when we consider in the following class, taking a particular example of any molecule. There we will consider the atomic orbitals, their wave functions, and we will operate these projection operators here. So, here like we say that this is particular irreducible representation J, right. Now, what we can do, we can take the real irreducible representation. So, you have to look at the character table, find out the irreducible representation that you want to work with. So, for example, some irreducible representation is B2U. So, you can have the projection operator written as P B2U. Okay. So, in the following class we also will see that there are two type of projection operator. One is like a complete projection operator, another is incomplete projection operator. So, for most of our purpose, we are pretty good with the incomplete projection operator itself, which deals with not the matrix element as such, but only with the characters. Okay. So, we can use the characters from the character table belonging to particular irreducible representation to form the projection operator, and thereby we can work on the particular orbitals of any atom within a molecule to project out which are the orbitals that can combine linearly to form the say Hybrid orbitals. Okay. So, in the following class we will learn more about this and try to form different SALCs for different molecules. Till then, have a nice week. Thank you very much.